Hey there, data explorers. Today we're diving into the exciting world of stock prices and the tantalizing possibility of predicting them. Imagine knowing whether a stock will go up or down. Think of the possibilities. This is why predicting stock prices is so captivating. It's like peeking into the future of financial markets. But hold your horses. Stock prices are influenced by a dizzying array of factors. These can be economic indicators, company performance, even global events. It's a complex dance of variables. That's where data analysis comes in. By crunching historical stock data, we can begin to unravel these intricate relationships. We can search for patterns and trends that might give us an edge in the market. Data analysis empowers us to make more informed investment decisions. It helps us move from pure speculation to calculated risk-taking. Remember, knowledge is power, especially in the world of finance. Now, let's introduce our secret weapon, linear regression. In the realm of predictive modeling, linear regression stands out as a simple yet surprisingly powerful tool. It allows us to model the relationship between two or more variables. We do this by fitting a linear equation to observed data. Think of it like this. We're drawing a straight line through a cloud of data points. The goal is to find the line that best fits the data. This line represents the relationship between the variables. We can then use this line to make predictions about future data points. In the context of stock prices, linear regression can help us understand how a stock's price might change based on factors like past performance, trading volume, or economic indicators. It's like having a crystal ball, but instead of magic, we're using math. Before we dive into the math behind linear regression, let's visualize what we are trying to achieve. Imagine plotting a bunch of data points on a graph. Each point represents a different observation. For example, we might plot a company's stock price against its earnings per share. If there's a linear relationship between these variables, we'll see the data points cluster around a straight line. The stronger the relationship, the closer the points will be to the line. This line is our line of best fit. It represents the linear equation that best describes the relationship between the variables. Now, not all relationships are perfectly linear. Sometimes the data points might be scattered, forming a cloud with no clear linear pattern. In such cases, linear regression might not be the best tool for prediction. But when a clear linear relationship exists, linear regression can be incredibly insightful. All right, let's get our hands dirty with the math, but don't worry, it's not rocket science. The core of linear regression is the equation for a straight line y equals mx plus c. You might remember this from high school algebra. Let's break it down. Y is the dependent variable, what we're trying to predict, like stock price. X is the independent variable, the factor influencing stock price, like earnings per share. M is the slope of the line, how much y changes for every unit change in x. C is the y-intercept, where the line crosses the y-axis when x is 0. The slope, m, tells us the direction and strength of the relationship. A positive slope means as x increases, y also tends to increase. A negative slope means as x increases, y tends to decrease. R squared, R2, measures how well the line fits the data, ranging from 0 to 1, with 1 being a perfect fit. By finding the values of m and c that minimize the difference between the predicted and actual values of y, we can create a model that predicts future stock prices based on the chosen independent variable. Section 5. Preparing your stock data for analysis. Before we can unleash the power of linear regression, we need to feed our model some high-quality data. The saying, garbage in, garbage out, holds true here. If our data is messy, our model will be unreliable. First, we need to select the right data. This includes historical stock prices, trading volume, and any relevant economic indicators. We can often find this data from financial websites or APIs. Once we have our data, we need to clean and prepare it. This involves dealing with missing values, converting data types, and handling outliers. Data cleaning ensures our model receives the best possible input. Section 6. Fitting a linear regression model in Python. Now comes the fun part, building our linear regression model. Python, with its awesome libraries like pandas and scikit-learn, makes this a breeze. First, we import the necessary libraries and load our cleaned data into a pandas data frame. Then we split our data into training and testing sets. This helps us evaluate how well our model generalizes to unseen data. Next, we create a linear regression model object using scikit-learn and train it on our training data. This process involves finding the optimal values for m and c in our linear equation. Import pandas as PD from sklearn.linear_model. Import linear regression from sklearn.model_selection. Import train_test_split x =, data, earnings per share, y =, data, stock price. x_train, x_test, y_train, y_test equals sign train test, split xy, test_size equals sign 0.2, random_state equals sign 42. And voila, we now have a trained linear regression model ready to predict stock prices. Section 7. Interpreting regression results. With our model trained, let's decipher what it's telling us. The slope, or m, reveals the relationship between the independent and dependent variables. A positive slope indicates a positive correlation, while a negative slope indicates a negative correlation. The r-squared value tells us how well our model fits the data. An r-squared of 1 means a perfect fit, while a value close to 0 means our model doesn't explain the data well. However, it's crucial to remember that correlation doesn't equal causation. Just because two variables are correlated doesn't mean one causes the other. Always be critical of your results and consider other factors that might be at play. Section 8. A practical example with real stock data. Let's see our linear regression model in action with a real-world example. We'll use historical data for Apple Inc. or AAPL stock. We'll try to predict Apple's closing stock price based on its trading volume. We'll follow the same steps as before. Load the data, clean it, split it, train our model, and then evaluate its performance. We can visualize our results by plotting the predicted values against the actual values. By analyzing the slope, r-squared value, and the visual representation of our model's predictions, we can gain insights into the relationship between trading volume and Apple's stock price. However, it's crucial to remember that this is a simplified example. In reality, numerous other factors influence stock prices. Section 9. Applications and limitations of linear regression in stock prediction. Linear regression, while a powerful tool, isn't a magic bullet for stock market domination. It's essential to understand its limitations. Linear regression assumes a linear relationship between variables, which might not always hold true in the chaotic world of finance. Additionally, it's sensitive to outliers, and past performance isn't always indicative of future results. Despite these limitations, linear regression can be a valuable tool for investors and analysts. It can help identify trends, uncover relationships, and make more informed investment decisions. However, it's crucial to use it responsibly and in conjunction with other analytical techniques and a healthy dose of common sense. So keep exploring, keep learning, and remember, the stock market is a complex beast. Linear regression is just one tool in your analytical arsenal. Use it wisely, and who knows, you might just crack the code to financial success.